Good afternoon, everybody. We're all in our slow down mode. Everyone's had plenty of
nap time,
food to eat, and nap time. I appreciate the opportunity to come and present this very learning community. And I was going to go last year to Nashville. It was within Indianapolis's driving distance, and fortunately I had a family commitment, so I couldn't make it last year. So I'm very excited to be here this year. Appreciate it. So one of the things that I decided to do is I had started getting this odd collection of calculators, and the Woodstock series is one of the series that really was close to home to me for very special. And I think I talked to several people who have had HP-25s as one of the first calculators that they ever had. So I started collecting, and the HP-29C, I was fortunate enough to get one off of eBay, and I'm very excited about it. But probably as many of you have experienced, you get it in the box, you open the box up, you're excited, you check it out, you replace the battery, and lo and behold, you either get no display or you get some funny zeros popping up on the display, and all of a sudden realize that none of the keys work on it, and your initial excitement starts to level off and starts to head south all of a sudden, right? So one of the things that I decided to do was look on the internet and look up information on 29C and see what I could find. There's quite a bit of information out on Woodstocks, and I'll certainly acknowledge this at the end of my presentation. Some very helpful people have given me information, but specifically on the 29C, I couldn't find the kind of information that I really was interested in. And I have a electrical engineering background, so I thought, well, let me dive in and get some things going. So I'll flip through a couple of slides. Let's go this first one. So the 29C is one of the last of the Woodstock series. Some of you probably know this. Developed in '77. It's only out 2 years. By 1979, HP decided to discontinue it. Part of the reason was the 67 was coming out and really competing with this, and obviously the 67 had a lot more capability, a lot more power than the 29. It was codenamed Bonnie, along with its sister Clyde, the 19C, and which is the printing calculator. So we're going to talk a little bit about my diagnosis of this, a little bit about my process of going through this and discovering how to restore a product. So we'll go to the next one. So that's just a little bit of the agenda, and we'll cover these topics. So for the next one. So word of caution, and you've seen, if anybody's seen Katie Wasserman's diagrams, do not plug in your power supply to this without having a battery in it, or a good battery, or just generally probably just never plug it into this. This is probably the best idea. Charge your NiCads or your lithium ions outside of this. You don't want to, because there's HP made a kind of a poor choice as far as the way that they designed the power supply section. The AC charger comes in, it presents 10 volts in here. It depends on the battery really acting as a load to this. So if your springs on the battery are bad, if your batteries are run down and depleted, or if the batteries just aren't making good contact, chances are you'll pass that 10 volts right through the circuit, and you'll get the funny display, or you'll get the no display on your HP, on your Woodstock series. So just remember, never plug that AC into it. Try to find either an old kind of broken calculator that you can use just to charge batteries, or you can just simply use alkaline batteries. I mean, the batteries aren't high enough voltage for alkalines to destroy the part. Next one.
Is that true for some of the others, like the 67 and the 35, that series?
I haven't done the analysis, Roger, on that. I think they did a better job on that power supply circuit. So.
Is it possible to kill some of these lights so we can see the screen a little better?
That would help, yeah. The lights near the front.
The 19 would be the same situation. Yeah, you wouldn't want to plug that in. So a little bit about setting expectations. What this presentation is a discussion of my passion and interest in vintage HP calculators, the sharing of information of things I couldn't find on the web, troubleshooting methodology, bringing the 29C back to life, and a brief contrast and compare. I've got a section just at the end on previous calculators and modern day calculators. What it is not is an in-depth discussion of the operation of the 29C. It's not a critical examination of the rooms, ROM routines, or the creation of the device itself. So, go ahead to the next one. So just a little bit of history I've already given you. So I originally got the 1811 model first. That was bad. The second one I got did not work either. So I'm thinking, wow, I'm batting 1,000. Neither one of them worked. So that's not a good sign. So just a little bit of interesting note down the bottom. You know, I track 29Cs on eBay. If you bid on a 29C, you're probably bidding against me. Unless it's got up to 345, and I don't go that high. So, yes.
I noticed one's continuous memory and the other one isn't. I thought they used two different.
Actually, it is continuous memory. One thing you learn too late is you never use alcohol to clean toothpaste because it will take labels off. And I unfortunately learned that just a little too late for that one. And I.
That's vaporware.
The memory did disappear also.
29Cs, I try to track prices and see what they're selling for. They range anywhere from $81 up to well over $300. The average sell price for the last year is about $200 on eBay, and I think this one sold brand new for $195 back in 1977.
There's a 19C, we got Northern Virginia for $395.
I see that one.
Fully functioning.
Yes.
Not me. Not his name.
Okay.
His name is Nick.
Next. So a little bit about disassembly. Disassembly is straightforward on this. It's a really easy product to take apart. There's a little bit of a lip on the bottom of it. You got to kind of separate with your thumb. Clamshell comes off from the back, and it's then the main PC board separates from the keypad very easily, and then you've got the display that pulls off as well. So this one actually has the ACT chip taken off the bottom of it, but it's very simple, very straightforward, and you'll see in a little bit that there's actually two different power supplies that they've used on these two different units, and I'll highlight that a little bit. So it's very easy to get apart, very easy to work on, very easy to reassemble, and pretty much nice through-hole components, so you can get test probes on it very easily. Just a little bit of a close-up, and we're going to talk a little bit about three areas. So we're going to talk about these ICs down here, area 1, area 2, which is power supply, and then we've got the cathode nano drivers up here, and that's just an obverse backside view of the same PC board. So just identifying the ICs on the board. You've got the arithmetic control and timing chip, or the ACT chip, which is basically the microcontroller that brings. Interesting enough, this is all serial data that pumped around. So it's kind of an interesting technology that HP employed. You've got 3 ROM chips, and actually there's a ROM-RAM chip on the third IC. There's on the 29C, since they were continuous memory, they had RAM chips. So these two were static RAM chips. Interesting enough, they were in side brace ceramic packages, which is a very expensive way to package things. But apparently HP was buying those at the time, and they weren't available in plastic. So
HP made them.
They did make them. Is that true? Okay. So usually, a lot of times, since this one's closest to the battery, if you've got any corrosion, you're going to find corrosion down in this area too. So, all right, we'll go on to the next slide. And this is just a picture of the power supply unit. It's interesting. This the second one I had has a little daughter board on top of it, and subsequently after that, it looks like HP had actually created that on the main PC board. So they went away from the daughter board. Obviously, a cost-cutting range for them. Looks like they did some simplification, but they moved some of the voltages around. So I'm actually doing some analysis on the power supply, and so hopefully maybe in another session in the future I'll have a little more analysis on the power supply, how it generates the voltages, and how the power supply works. Jacques Laporte has done some really nice work on the power supply. Jacques got some very good analysis he's done on some of the earlier Woodstock models. So there's some Zeners in here, but I haven't fully deciphered all of the parts yet. So I'm going to try to get that done with some work. So going on to the next one. So at the top of the PC board, you'll see the anode driver and the cathode driver. So they're both driving not only the display, and there's it's basically multiplexing through the displays and through each segment. So it's very rapidly painting, whatever digits are, called by the ACK chip. There's also, this actually does a keyboard scan as well. So it's actually half of the keyboard scan for rows and columns. And I don't think I put the detail in there, but if anybody's interested in that, I can talk about that at a later time or give you more information on how that works as far as the keyboard scan. Okay, this is one thing that I went and created. I received a hand-drawn diagram of this, but it wasn't complete. And this was really frustrating to me because I really couldn't get down and discover what are the pin IC numbers, what are the functions for each one of them, and what do they do and what they do through the circuitry, and where do I need to really measure to decide how to debug and how to try to bring this back to life again. So this is one of my own original creations, and it's, certainly want to make it available to anyone here or anyone else that would like to diagnose their own HP Woodstock product. So it's a pretty complete drawing. It doesn't have the power supply. I'm still working on the power supply portion of that. So hopefully, in the next 3 to 6 months, I'll have that done and have a little more detail on it. But this shows the keyboard. It shows the keyboard scanning on it. The signals, I know it's too small to read, so I apologize for that. So you'll have to blow it up in your package that you got on your flash drive. But it's got the cathode driver and the keypad driver, and you saw those signals come over here, and they scan on one side on the rows, and then there's a column scan that comes actually out of the ACK chip for the processor. So between doing all that, because you're pressing a key, it decides what to do from there and display, either display or executing a function inside of it. And the displays down here, and it's got a whole series of pins along the top that it connects. So a little bit about kind of the troubleshooting and diagnostic process that I went through. I noticed that the first unit that I got was not functioning, as I said before, and it was just displaying random zeros, and which usually is not a good sign. None of the keyboard presses would do anything, and I usually use a bench power supply. I've got regulated 2.5 volts, so I'm not using batteries at this point, so I really take the batteries out of the equation. Suspected that one of the ICs was bad, so went through and tried to do some diagnosis. I started unsoldering some ICs off the board, and really was unable to, just with a single unit, really able to do much diagnosis other than really kind of look at the power supply. Power supply gave me some clues when I started to look at some of the information I'd received from Jacques and from a few other people, and decided it looked like the power supply voltages were almost right, but not quite right. And certainly the display wasn't correct. And so I did go in and I acquired a second unit a few months later, and I swapped the cathode and anode drivers between the two. And I thought, gee, the first one didn't have a display, the second one did. Maybe it's just cathode anode drivers. Well, that didn't seem to fix anything. So the next thing I did is I said, let's go back to some fundamentals. I had an HP-25, and I said, let's look at the ACT chip on the HP-25, and let's really get some idea of what the oscilloscope signals look like coming out of that. And I had some information on that. It's got a dual sync signal that comes out of a Phi1 and Phi2. There's an oscillator. It's a tank oscillator that's easy to get to. And then there's some other signals, the sync signal and the data signal, that are pretty similar between them. So measured the original calculator that I'd received, and found that the amplitude was low. It should be around 18 volts peak to peak. wasn't close to that. It was half of that. So I said, okay, there's something looks strange about that ACT chip. So I installed. I actually took the second calculator and I put all low profile sockets in it, so I could actually install a IC and either put it in or pull it out. So it just helps me diagnose it. Was actually able to put them all back inside. I had to do some milling on some of them to get the XY coordinates close enough to each other so I could put them next to each other, but it fit all back inside. So I've got a nice calculator that's all socketed now. So go on to the next one. Just a little bit about the power supply, and I don't have a picture of the second one of where the single board version, but on the daughter board version, the one that was operating, you're going to see there's a VSS display that drives, or a VSS voltage that's coming off this capacitor. That gives you your power supply voltage that's always on, that keeps your RAM alive. So that's your continuous memory. So it keeps your RAM alive as long as your battery's in there. Now, you've got continuous memory, you won't lose your programs if you shut it off. You've got a V display voltage. This is around 4.37 in that area, plus or minus 10%. And that's coming off the end of this, it's accessed off the end of this diode. You're seeing excuse me, here's the VRAM. I'm sorry, this was the main driving voltage over here. VRAM chip is 6.5 off this diode. You got this tank oscillator circuit that's just an inductor and a capacitor, and they hook up to a tank circuit inside the ACT chip. And I'll show you some waveforms on the next one. But and then you've got the switch battery voltage that'll whatever your batteries are charged to. So that's coming right off this filler capacitor. So if you measure those voltages, if you happen to diagnose probably any of the wood stocks at this point, other than the VRAM display, you're going to get these plus this minus 12. So you're going to get all these voltages. If you have that, chances are your power supply is good, in good shape. So go to the next one. So a little bit about where to measure these. So here's again our PC board. You got the arithmetic control chip. You got the tank oscillator on pins 13 and 14. And you just take an oscilloscope, connect your ground lead up, and you measure this, and you're going to measure a nice, can't see the scale here, but you'll measure a nice nice sine wave coming out of it, pretty nice sine wave coming out of it. If you've got that, then you know your oscillator's working, your ACT is probably in good shape, but just as a good verification, to see the Phi1 and Phi2 signals coming out, these should be 18 volt peak to peak voltages, and those are going to come out of pin 16 and 17. So if you've got access to an oscilloscope, it's a great way to look at it. I've got some other signals on the addendum of the sheet that I probably won't show today, but they're there for your, if I've got time I'll show them. But, so if you measure these voltages, good chances are that your ACT is in good shape. You haven't blown it out by plugging your AC charger in without a battery, and there's a good chance that this is probably a good board that's operating. So you've got your voltages and your oscillator, and you've got Phi1 and Phi2 that are pumping down around the board, pumping data around. Next one. So really, at this point in time, I took the ACT from the first calculator. I supplanted into in the second calculator, turned it on the power switch, and I had a single 0. Now, in the meantime, I'd taken out all the ICs. So there were no RAMs, there were no ROMs in there. So it was interesting that once I plugged in the ROM chips, I did get the 0 that lit up in the left-hand location, far left-hand location. Wow, much better than before, because I just had random zeros popping up. So plugged in the 2 RAM chips, and it shows an error. That error is common in these series of calculators. If you take the battery out and you let it discharge, and you put a battery back into it, it'll show error. You hit a key, and that error clears, and you'll get the nice 0.00. Well, bingo, there it was, eureka! I got a functioning HP-29C. So any engineer's dream is to get to the final solution, right? So it was great. So I continued test functions on the 29C, tested the programming samples in the book, and so I was really very, very pleased to get a fully functioning unit. Next one. So just a little bit wrapping up the discussion. I did a little bit of contrast and compare against to just one of my favorite calculators, the 34S these days. So you look at what the 29C had capability. It had 98 program steps, 30 storage registers. You compare that to 928 steps on the 34S today, 107 global registers and 112 global user flags, 6,000 program steps in flash memory. You had 4-level stack here. Basically, you have 8-level stack here, and the stack is really unlimited on the 34S. 34-digit decimal accuracy, and then versus you had rechargeable batteries here, disposable CR2032s on this calculator, and then obviously the whole host of math and functionality that you have in this. Certainly not that you can't program some functions into here, but obviously you've got a huge wealth capable today, and obviously the HP Prime extends that even further. So, just as a summary, conclusions to this presentation, the goal is really to kind of share with you my experiences of how to restore this particular series of Woodstock calculators, give you some clues of what to look for if you decide to take it apart. Again, like I say, it comes apart very easily and pretty robust. These are NMOS and PMOS circuits that aren't quite as sensitive to static. The CMOS are going to be a little more subject to static electricity.
The CMOS one's a lot.
Yes, so you don't want to try to be handling the CMOS portions of it too much. So you've got quite a robust PC board to deal with, and so there's some diagnosis you can do. Just look at the overall condition of it, clean the PC board if it needs to be cleaned, measure the 4 power supply voltages, a little bit of investigation on the ACK chip to see if you're getting the oscillation and the data clocking circuits. And if the ACK's damaged, you're probably going to have to find another donor IC from another calculator. So finally, I think the restoration of these fine pieces of history is satisfying. It's rewarding, and we're taking a 30 to 40-year-old calculator, we're extending its lifetime in the future. In fact, the keyboard on this is still very, very good, very solid. So just showing you it does in fact turn on. So thank you very much. Oh, by the way, yes, this is my final slide. I really want to acknowledge Tony Duell, and I've heard his name. I know a lot of you, or most of you, probably know who Tony is, and he's just a wealth of information. He and I exchanged quite a bit of information back and forth on this series. Jacques Laporte, same thing. Jacques got a lot of information. He's got a website that has a lot of information on it. In fact, you'll find a dialogue between Jacques and myself about this particular calculator. Certainly Museum of HP Calculators, Jeff Quickfall, he and I have exchanged a number of emails. Dave Culver over in the UK helped me, sent me some hand-drawn diagrams of the schematic. And then Randy Sloyer, I think some of you know Randy as well. He runs Fix That Calc. Eric Smith, and then certainly Katie Wasserman has some really good information on power supply information in the batteries. So I really appreciate all those help, and hopefully I contributed just a small amount of information to this. So thank you very much.